We are in Washington State learning all about volcanoes and earthquakes.
Because it's not a matter of if one of the Cascades volcanoes is going to erupt again, but when. This is STEM in 30.
40 years ago, Mount St. Helens exploded,
sending 450 million tons of ash into the air while blasting a 250-foot crater.
This was the most deadly and costly volcanic eruption in U.S. history. The eruption of Mount St. Helens was a huge disaster, but the scientific information we collected is still keeping us safe today.
This is an active volcano behind us. Should we be standing here?
Well, I don't know, but let's head over to the Cascades Volcano Observatory and find out.
Welcome! We are at the U.S. Geological Survey Cascades Volcano Observatory, and right now we are in the ops room of the observatory. So this is where we observe where monitoring data is coming in from each of our volcanoes here in the Cascades.
What exactly is a volcano?
A volcano is a place where magma is coming from the deep earth to the surface, where magma becomes lava or explosive pyroclasts. And pyroclasts are just the word that we use for volcanic rocks that explode out of the volcano.
What are we seeing on the monitors back here? There's data coming in as we talk. What's going on?
There's data coming in from each of our major 10 volcanoes in Washington and Oregon, and we have seismometers that measure ground shaking. So we can feel or detect when the ground is shaking even a tiny, tiny little bit from each of the volcanoes. We also have data coming in on volcanic gas and sound waves. Sometimes if volcanoes have rockfall or if they have eruptions, they produce sound waves that can be detected.
Do you watch all 10 volcanoes 24/7?
Pretty much. They have permanent sensors that are located on them, and that means that any ground shaking at all can be detected. And the more seismometers, the better.
Why is it important to continually monitor these volcanoes?
Well, we want to continually monitor our volcanoes so we can see if any of them start to wake up. Because at the moment, all of our 10 major volcanoes are quiet. So they're still active, they're just in a quiet background state. So what that basically means is that we want to be aware of any changes so we can figure out when our volcanoes erupt, which one, and what's it doing exactly.
If one of the volcanoes woke up, what would that look like?
It could take a number of different paths. One possibility is that there could be a little bit of unrest, so ground shaking from magma movement or bursts of steam, and then the volcano could just go right back to sleep and nothing extreme ever happens. Sometimes a proper eruption can ensue. So for example, in 1980 at Mount St. Helens, there were months and months of unrest at the volcano, and then the really cataclysmic eruption happened on May 18, 1980 with volcanic ash plumes that went 32 kilometers into the atmosphere. So many, many different scenarios can occur, and that's why we have constant monitoring and scientists who are trained in uncovering the behavior of each of the volcanoes.
Is there any way to pinpoint a time when one of these eruptions might happen?
Yeah, when's it gonna happen?
When's it gonna happen? So there are two approaches to this. One is to understand the geology of the volcano. So by going back in geologic time, by uncovering the layers that are preserved from each of our volcanoes, we can get a better understanding of how they behave through time. The other side is the monitoring. And so this is why it's so important to have both field geologists who study the ancient history and behavior, and also people who are ready in real time to detect ground shaking from earthquakes, changes in gas content or gas abundance, and all the other signals that could happen when a volcano wakes back up.
The Earth isn't the only place that experiences seismic activity.
The InSight lander on the surface of Mars is looking at some of those same things.
What Mars InSight lander is going to allow us to do is really map the inside of Mars. The one thing that really excites everybody is a question that we ask ourselves over and over again, which is, are we alone in the universe? Is there potential for life on a planet that's not our own? If we want to get as much science as we can, as fast as we can, we need to get really good at using robots. We're going to have robotic missions to the moon before we have humans go to the moon so that we can get the most out of our human science missions. And that's true on Mars as well.
InSight is a mission to study the deep interior of Mars. It has many science instruments to do this, one of which is HP cubed, a sort of planetary thermometer. A key component of HP cubed is called the mole, sort of a self-hammering nail that drives its way into the ground. This is unexplored territory. The mole is going somewhere we cannot see and have never been before, to get that crucial number, the heat flow of Mars. As a scientist, I want to get that number.
We're getting the first sounds from Mars from our instrument, and we're realizing it's picking up vibrations from the air that are then, sort of being transferred from the spacecraft to our instrument. So the sound comes in, which are, pressure variations. They vibrate these big solar panels on the spacecraft and other components as well. Those vibrations then are picked up by the seismometer as it's a vibration sensor and turned into electrical signals, electrical impulses that we can then send to Earth and then put back through an amplification system into a speaker. That speaker then recreates the pressure pulses, the pressure waves that we're sensing on Mars.
This is an important mission, not just for the United States, but an important mission for the world, so we can better understand why planets change and ultimately understand even more about our own planet.
Alexa, what is this?
This we call the spider. This is an instrument that we use to monitor areas, especially volcanoes, that are unsafe for people to go. And it's monitoring three major things. One is seismicity. Go ahead, take a jump and see if we can see that on the screen. We also have a system on the spider to measure infrasound, which is a type of sub-audible sound because volcanoes make sound waves. The infrasound frequency of that energy can propagate really far, so it's much more easily detectable than the type of sound that we make with our own mouths.
So if I just yell, it's not going to pick it up because this is recording sound that's too low for the human ear to hear.
That's right. So as you talk, the infrasound detection isn't really going to pick up our voices, but it will pick up a lower frequency pressure wave, sound wave, which is what is created by whooshing at volcanic eruptions.
Now, there's a third thing that we have to look for.
And the third thing we have to look for is volcanic lightning. One of the ways that we can detect that is by making an electrical spark that can be detected by a little radio antenna. And so if we create a little spark as a fake volcanic lightning, we can see that it's detected. Wow. Having three different types of data for volcanic activity really helps us figure out where the ground shaking is coming from, whether it's rockfall, whether it's an explosion, and whether there's ash in the atmosphere that's creating lightning. And that's important because it can affect jet aircraft.
Now, see that one of these things is hooked up and one of them looks like a fishbowl.
This fishbowl is what's inside of the seismometer sensor here. So this whole system, the spider gets dropped by a helicopter inside the volcanic crater or any other place that's unsafe for people to spend a lot of time in. And it's not a permanent station, it's a short-term fix to fill in gaps in data that don't exist from the other stations. But what's inside of here looks essentially like a fishbowl because the seismometer needs to be oriented vertically, and if it's just dropped by a helicopter, it could land in any position. So by having it suspended in silica gel, it can move to a vertical position no matter how it's landed inside the volcanic crater.
So all of this is to collect data on an active volcano.
That's right.
Let's go over to our science correspondent to learn more about data collection.
Somewhere over Mars, the Mars Reconnaissance Orbiter silently stands watch over the red planet. Down on the surface of Mars, the InSight lander collects data about the surface and what lurks below. Combining the data from InSight and MRO, scientists are able to learn about the inner structures of Mars. Scientists looking at data collected by the seismometer see how the surface of Mars is moving at the InSight landing site. On Earth, earthquake locations are triangulated by using at least 3 seismometers. On Mars, there's only one. When the ground shakes, it could be the wind, it could be a meteor strike, or it could be a Mars quake. When an anomaly is detected, the seismometer team works with the weather team to see if anything might be causing it, like wind. Bringing the data together not only helps the seismometer team, but it also helps the other teams understand the full picture of what is happening on Mars. If an anomaly cannot be identified as a weather event, the seismometer team can check with the Mars Reconnaissance Orbiter team to see if the cameras have detected any new craters on the surface that may have contributed to the anomaly. More data collection and investigation continues to help paint a vivid picture of what Mars is like and possibly what it used to be like. When all of the anomalies have been accounted for, some can be attributed to Mars quakes. Studying these seismic events help us learn more about what's going on inside the red planet and ultimately help us know more about our planet.
Wow, Alexa, this looks just like a papier-mâché volcano a middle schooler would make for a science fair. What's going on here?
Well, it is a papier-mâché volcano. Research geologists, we love our papier-mâché volcanoes just like anybody else. So the reason we have this is that it's a very simple scaled replica of Mount St. Helens, but really what's underneath is what's interesting, because this is a little demo, a little demonstration that we use to show how volcanic plumes rise up into the atmosphere. So, for example, we're really interested in how fast volcanic plumes rise, how they widen as they extend up into jet airspace, and we're really interested in turbulence. So that's how these eddies entrain air as the ash plume is rising up through the atmosphere. So we do laboratory experiments and numerical simulations using computers to study how that works.
Alexa, why is it important for aircraft to know about this plume?
Well, volcanic ash is dangerous to jet engines. And so we really want to be able to keep aircraft safe out of the way of volcanic eruption plumes. But if we really want to look at that, we should look at some volcanic ash under the microscope in the lab.
Oh, that'd be cool.
Let's go.
Let's go.
Okay. Here we are in the lab. Now, I've got a sample for you. What do you think this is?
Salt and pepper,
Yeah, it looks like just like salt and pepper.
metal shavings.
This is volcanic ash. So you were asking about volcanic ash and why it's hazardous for jet aircraft. Well, this is what we can look at. Volcanic ash is different from the ash you see in wildfires. It's different from smoke because that's made out of burnt up plant material. That's not in volcanic ash. Volcanic ash, well, you tell me actually, Marty, put it under the microscope there. What do you see?
Oh wow, it's like sparkly and it almost looks bubbly. That is cool.
Yeah.
And it's white and black and all kinds of different shades.
Right. So what you're seeing there are all pulverized pieces of magma. So it's all volcanic rock. So that's what volcanic ash is. It's pulverized rock that originated from the magma deep under the volcano.
And what does it do to jet engines?
So the reason this is unsafe for jet engines is that the volcanic glass melts. It has a low melting temperature. And when glass melts inside an engine, it can make the engine overheat and it can be really unsafe for the people inside the airplane.
But when a volcano goes off, that's a big event, and everybody knows about it. Why can't they just fly the airplanes around it?
Well, there are actually eruptions happening every single day. So we don't always know every single eruption that's happening around the world. There are more than 1,500 volcanoes on the planet that are active at any given time. And so there can be multiple eruptions happening during the day that we might not necessarily know about. That's why it's so important to coordinate with atmospheric scientists and volcano scientists so that we can have a better picture of how to reroute aircraft.
Now, the Mount St. Helens explosion looked a lot different than the one that recently happened in Hawaii. Why is that?
Okay, to answer that question, we should really look at the rocks. So here's a good example. Okay, so this is volcanic ash from the 1980 eruption of Mount St. Helens. And you can see that it's tiny particles of volcanic ash. So that eruption was so explosive that it blew apart the magma into tiny, tiny pieces. It was really full of gas because gas is what drives the explosiveness of an eruption. Now, at Kilauea in Hawaii, which erupted so recently, there's not as much gas in the magma. And so that story is recorded in the rocks. And we can look at that here. So these are volcanic rocks. So these are actually called golden pumice from Kilauea during the 2018 eruption. And this is very different from the volcanic ash we just looked at. See, hold this in your hand.
That's not a rock, that's styrofoam, right?
This is a real rock.
It's so light.
It's so light because it's mostly made out of bubbles. And these rocks came from the really high lava fountain from Fissure 8 at Hawaii in 2018. And this is important because it's really the bubbles inside the rocks that tell the story. So even though there was clearly some gas in the eruption, because we see all the bubbles, that's the gas that was left behind, it wasn't gassy enough to blow itself apart into tiny pieces of volcanic ash like Mount St. Helens.
So even though this looks like it's got all these bubbles and gaps and spaces in it, the ash actually shows us that there was more gas in it because it blew it apart.
Because it blew it apart, whereas these are bigger chunks. It didn't blow itself apart quite so effectively.
If you just saw that or picked that up, you would think it was a piece of styrofoam.
I know.
And this is really how we do geology. We use these samples that we collect from the layers in the geologic record to tell the story of what happened during the eruption that made them.
So you're a rock storyteller.
They're like books to geologists.
We've learned a lot about volcanoes from rocks.
But we also got a chance to talk to somebody that had an out-of-this-world view of plate tectonics. Check it out.
Today, I'm joined by Dottie Metcalf Lindenberger. Dottie, thank you so much for being here. You were an astronaut,
Yes,
a teacher,
yes,
and a space camp graduate, correct?
that's right. Yes, that's all right.
And you also study geology.
Yes, currently a geologist.
You live in Seattle,
Mm-hmm.
so you have the Cascade Mountains.
Yes.
So we're going to ask you to talk about plate tectonics.
The interesting part about the Earth is that, of course, there are parts that act very brittle. That's our top crust part that we're going to be using here. And we call that, for a fancy name, the lithosphere.
Okay.
Litho meaning rock. And then there's the mantle below, and the mantle has a portion on the top of it called the asthenosphere that is a little bit plastic. So we're going to put that as our icing. It acts a little bit plastic. Okay, so our lithosphere is on top of our more plastic asthenosphere, which is really a part of, like we talked about, the mantle, which now we have this bottom crust, but it goes a long ways down.
Okay.
So on this brittle part at the top, we have things that act like plates. That's why we call it plate tectonics. And the plates move in different ways. We'll start out with plates that move past each other. This is what we call transform. They're transporting past each other.
Okay.
When they do that, as you can see, it really grinds up the crust. And ours is moving along a nice line, but rock doesn't behave nice, and it goes through, and sometimes it hangs up, and then when it pushes past, there's a big break, and that can cause some pretty significant earthquakes. And obviously it's at the top of the crust, so people really feel it.
Now, can you see something like this from space?
Yes, you can see the San Andreas Fault from space. You can even see it flying. So we should probably talk about then divergent, because you're creating crust. And so these plates are doing exactly like we said, they're diverging. And when they do that, this asthenosphere is coming up and making lava, and it cools rapidly if it's underwater, really rapidly. And it creates more plate. In our model, there would be more plate being created behind it. Where there's divergence, there's also somewhere around the world has to be convergence. And convergence happens in many different places. There's both ocean crust and continental crust. Of course, we tend to live on continental crust. So where I'm at in Seattle, we have convergent plates. And what we have is an ocean plate that's going underneath continent like this. And when it does it, it of course scrapes along the base. And we have a set of mountains that are forming because there's sediment being scraped off. Those are called the Olympic Mountains. But behind, as this scrapes down, it starts to melt as it goes into the asthenosphere. And we have a line of volcanoes that form behind that. So Mount Rainier, Mount St. Helens, Mount Hood, all of those are famous Cascade volcanoes that are still active. And as we know with Mount St. Helens, very active. And convergence also happens between two continent plates. And when two continents crash, neither one wants to go under. They're less dense. They want to just keep pushing up. And I can't do this very well with graham crackers. They're gonna push and make these huge mountains.
Thank you so much for explaining this to us.
Yeah, it's so much fun, and it's a tasty snack, right?
Yeah, now everyone can have a snack. How is it?
Pretty good.
Back in the Pacific Northwest, we headed out of the mountains into the city to visit one of America's most iconic landmarks. We're at the Space Needle in downtown Seattle.
The Space Needle was built for the 1962 World's Fair.
And it is over 600 feet tall.
It is also built to withstand high winds and even earthquakes. You ready to go up? Come on, it's gonna be fun. Let's go. Come on, Marty. When it was built, the Space Needle was the tallest man-made structure west of the Mississippi River.
Because of its place in a subduction zone and its proximity to the volcanic Cascade Mountains, the Space Needle was built to withstand earthquakes of up to 9.0 magnitude and winds of up to 200 miles per hour, like those found in a Category 5 hurricane.
One way they did this was by digging a hole 30 feet deep and 120 feet across, and filling it with 467 trucks worth of concrete. This concrete foundation has the same weight as the above-ground steel structure.
The Space Needle, like most modern buildings, combines materials with different properties, like concrete and steel. These materials work well together. Steel is lightweight and designed to bend. Concrete, on the other hand, is much heavier and more rigid.
The concrete allows for high compression downward, while the steel allows for high tension being placed on the structure. Neither material will be good at the other's job, but using them together allows for a structure that is both solid and flexible, which helps it stand up to both earthquakes and wind alike. Despite surviving multiple earthquakes unscathed, Marty is still afraid of being 600 feet up in the air. Look at this. You got in the elevator, we got to 520 feet, and look at this view. The downtown Seattle area, Puget Sound, you can't beat it up here.
The view is incredible. It is really cool up here, and especially knowing that, it was designed to withstand earthquakes and high winds, that makes me feel a little bit better. Can we go down now?
Really?
Yeah. You can build your own structures at home. Let's go over to Liberty, Missouri, and Mr. Forsman. His kids are designing their own towers to see if they can withstand earthquakes.
Hi, my name is Eric Forsman, and I'm a teacher at South Valley Middle School here in Liberty, Missouri. And these are my boys, Jacob and Tyler, who also attend South Valley Middle School. Today, they have been working on some tower designs that they're going to create out of toothpicks and marshmallows. They've done a little research online on different designs, different components of a structure that make it strong, and their ultimate goal is to withstand an earthquake. They each have a design here. Jacob has been working on his. You can see he's got some triangles, side view, top view, and then Tyler has done the same thing here. We're gonna go ahead and get started on building the towers, and we'll see what we can come up with. So do you have any concerns right now?
It doesn't stainless do this because the toothpicks, like some are kind of poking out the bottom of the marshmallows. So it's not completely even.
What do you think of your design?
I think it's pretty good.
Anything that didn't go as planned so far?
The sides aren't exactly the same size, so.
Yeah. Obviously, we did not have the ability to go out and purchase a shaker table that you might see in some of the science classrooms, being that we're at home. So the boys actually researched and developed a little Lego shaker table. It's got a little ridge here that the towers will sit in, and then I will mimic the forces of an earthquake. All right, are you ready?
Mm-hmm.
So there was our first one. It stayed intact. However, foundation did come off and it did fall off, okay? Tower stayed together. However, it did fall over. So based on what you guys did, let's have a little brainstorming here. What would you guys do different?
Create like a better way on the bottom to connect it to the, because I saw that it came off. So I think our like structure is good.
What have you guys developed to help you fix this problem?
We have a base isolation.
Developed out of Legos, and then what do you guys have for your isolation? How did this work?
So we have balls under here, which will help it like slide around more than and almost work as a bearing to keep it off. So then the whole building will move, and it won't be as it won't kill it as much whenever it is.
Okay, so you guys want to give it a shot?
Sure.
All right, let's see what happens. So I'm gonna start my earthquake here, and you can see not too bad.
No.
Once again, stayed together structurally, foundation fell apart. All right, Tyler, here we go. Same thing, same forces. Lasted longer. Okay, good. Based upon the amount of time you guys have, this is a great way to really refine the earthquake-proof structures lesson that you guys already do. With additional materials, research, and methods of testing, students can take this to the next level. Bottom line, this is real-world science, and don't be afraid to fail forward, fail, learn, and try again. Thank you.
We have run out of time here in the Pacific Northwest.
We have to say goodbye to all these beautiful views, but this beauty comes with a price.
We're lucky to have scientists like Alexa who are learning from the past to help us prepare for the future. Thanks for watching.
Look at the clouds.
Unbelievable.
One more stop, Marty. One more stop. You're gonna love it. I swear, Marty, you're gonna love it. One more stop, Marty. You'll be fine. It'll be great. You're gonna love this, I swear.
There is an awful lot of glass and that floor is moving.
Uh-huh. It is the rotating...